So we will continue today problems of chapter 18. Last time we have introduced the different equations in chapter 18. Today we will do some practice on these equations. So first, a cylindrical work part of 125 millimeter in diameter and 900 millimeter long is to be turned in an engine lathe. The cutting conditions are V equals to 2.5 meters per second. The feed is 0.3 millimeter per revolution, and the depth of the cut is 2 millimeter. We should determine the cutting time required and the metal removal rate. Okay. So first, last time we have introduced that the cutting time, or we can say also the machining time, can be calculated function of the rotational speed and the feed rate. Okay, so last time we developed an equation for the machining time. Now in this problem they gave us the dimensions first of the work part. So we know, so this is d equal to 125. We have the length L also, on which we are performing the operation. The turning velocity V. The turning velocity V will allow us to, in addition to the diameter of the cylindrical work part, will allow us to calculate the number of revolution per second. Because we have seen last time that N is related to omega, okay, to the rotational velocity. N is omega angular velocity over 2 pi. And we know that omega can be replaced by velocity, linear velocity over radius, because V here given is the linear velocity at the radius level. So here when you have an angular velocity, okay, the velocity given corresponds to the outer peripheral velocity here. So you can relate it to omega by V equals to omega times the radius of your work part. So by replacing omega by V over R, then you get that N is V over 2 pi R or V over pi D. Okay, so now we can get the value of N. Just we should pay attention for units. So in case we want to obtain the value in per second, then the time of velocity will be per second. And concerning the meters here, okay, so if you use for velocity meter per second, then you should use for the diameter meters also, okay, because you have to simplify the unit lengths, then you will get revolution per unit time. So in case we use in V meters, the same unit should be used in D or R. And concerning the time unit used for velocity will be the corresponding time unit for N. So when V is in meter per second and D in meters, then we will get that the rotational value N will be in revolution per second. Now, concerning the feed rate represents the advancing velocity of your tool during the operation. It's given here in millimeter per revolution. And you have the feed and you have the feed rate. To convert from, if you want from feed to feed rate, you can multiply, because what is the difference? The feed is, if you want, the advancing distance per revolution. So the unit is millimeter that I am cutting for 1 revolution of my work part. Okay, then if you want to deduce the value of the advancing velocity of your tool, which is the feed rate, then you should multiply F by N. Okay, since F represents millimeter per revolution and N represents revolution per second. So by multiplying F by N, the resulting unit revolution will be simplified, and the resulting unit will be in millimeter per second. Okay, so once we find the feed rate, we can now calculate the machining time. The machining time can be calculated then as the total length of cut, which is 900 millimeter, over the feed rate, which is the advancing velocity. So it's like you have delta T equals to a distance over velocity. Okay, So in this way, you can calculate the corresponding machining time. Now also just pay attention for units. Since you have calculated FR in millimeter per second, then the length should be in millimeter. And then when you do the ratio, the corresponding unit will be seconds. In case you want to convert it to minute, all you have to do is to divide by 60. So just pay attention for the units they are asking for in the problem. If they tell you provide the total time in minutes, make sure to do the required conversions. Okay? Now, concerning the removal rate, to get the removal rate, you should use the formula that the removal rate is the turning velocity times the feed rate times the depth of the cut. So all informations are already provided. We have V, we have F and D. Then we can calculate the removal rate. And just make sure, for example, here, V is given in meter per second, while for the other we have in millimeter. So, or we convert F and D to meter, or we convert V to millimeter, and then the corresponding final unit will be millimeter cube per second. Okay? Any question on this? Another problem. A drilling operation is to be performed with a 25.4 millimeter diameter twist drill in a steel workpipe. The hole is a blind hole at a depth of 50 millimeters, and the point angle is 118 degrees. The cutting conditions are a speed of 25 meters per minute. This represents the advancing speed of the drill. We have a feed of 0.25 millimeter per revolution, and we have to determine the cutting time to complete the drilling operation and the metal removal rate during the operation after the drill bit will reach the full diameter. So first, to begin with, let us remember the drilling operation. So you can see it. We can see it back here in the chapter 18 equations file. So we have already developed that we can also relate, in case of drilling, the velocity of rotation to the number of revolution per minute of the drill. Okay, so it's similar to turning. You have the peripheral velocity over pi d will give us the number of revolution per minute of the spindle. Now, also we distinguished two types of possible holes. If you remember, we have the through hole and blind hole. In this problem, I think they said we have a blind hole. Okay, so since we have a blind hole, then we are in scenario in part B. So depending on the scenario, what will change is the value of, if you want, the value of calculation for the total length, because when you have a through hole, the total length of the advancing length of the tool should be A plus the thickness. While in case of a blind hole, I should just add A to the depth of the hole. So concerning A, the approach distance can be calculated function of the diameter of the drill and the angle theta, where theta is the point angle of the drill, which is this angle. Okay, so here in this problem, they gave us theta, they gave us D, so we can calculate the value of allowance. And of course, they should give us what is the depth of the hole required. So if we go back to our problem, we have the rotational peripheral velocity is given by 25 meter per minute. From this velocity and knowing the value of the diameter, which is 25.4, we can calculate the number of revolution per minute required to perform the operation. And once we have the value of n, we can then calculate the value of the feed rate, because the feed rate, which is, if you want the advancing velocity, and you have two types of velocities. We have the velocity of rotation, rotational velocity, which is given here in the cutting condition, the speed. You have the velocity of the tool that is advancing inside the work part. So this can be calculated as the feed rate. The feed rate is equal then to n times the value of feed, because we have seen that as in the previous problem, the same equations apply. Feed rate, which is the tool advancing velocity, is equal to n, which is the number of revolution per unit time, times the value of feed, which is in millimeter per revolution. So in this case here, since already n is given in revolution per minute, and we have the value of the feed in millimeter per revolution, then when we replace in the feed rate, we get our result in millimeter per minute. And now to calculate the machining time, we should divide the total length over the feed rate. In the turning operation, the length was equal to the length of the cylindrical work part. So the tool will advance in this way to cover the whole length. While in case of drilling, what will happen? The drill will move perpendicular to the work part. Okay. Then in this case, the total distance moved during the operation will be equal to the approach distance A plus the depth of the hole. Now, in this problem, concerning, yes, this is the depth of the hole. They gave us what is the depth required. So now what is missing is to get the approach distance. So as we said, the approach distance in blind hole operation and also in through hole, and in both we have the same expression for A, but the difference between blind hole and through hole is that in case of through hole, we should add to A the thickness of the work part, while in case of a blind hole, we should add the depth of the hole. So here, A is given by 0.5 times D, which is here 25.4, times tangent of 90 minus theta over 2. So we replace theta by its value, and we have already the value of the diameter. So we can get the allowance. Now the allowance, the approach unit, is the same as D. So if you use D in meters, then the approach distance also will be in meters. If you use D in millimeters, then A will be in millimeters. Okay? So now we can calculate the machining time by dividing the total distance, which is A plus the depth of the hole, over the feed rate calculated. And then we can get the machining time. Now, they asked also for the removal rate during the operation after the drill bit reaches the full diameter. So concerning the removal rate, we have seen together that the removal rate is equal to the cross-sectional area of the drill for the full diameter times the feed rate.